In the second part of the lecture about type requirements, I'd like to show you how they can be used to constrain template specialization of certain objects. That is, using type requirements, we can allow, for example, only certain set of template parameters on a given class template. Let's look at an example. Consider a generic shape class whose template parameter is constrained to have only arithmetic type. Here, the class shape is a generic class and the template parameter t is constrained to work only with arithmetic type. And the constraint is a named concept defined above, which means the template parameters can either be only integral or floating point type. And now consider two other generic utility functions, create shape and move shape, that works with shape but whose template parameters u and v are completely unconstrained because they may be a third-party library and implementers probably don't have the complete picture of the constraint needed to make the utility functions compatible with shape class. The question therefore arises how to check if generic functions template parameters u and v can work with the shape object. As you might have already guessed, the client implementation of utility functions can check the template parameters u and v can create and work with valid shape objects by using a type requirements. In short, with the help of type requirements, we can check that the template specializations of a particular object is valid or not. Let's see this in action. Once again, be reminded that this kind of requirement is useful when the implementers of utility functions don't have the entire picture on the constraints on a given object. So let me create another named concept called shape constraint. And in the body of the concept, I use a type requirement. And as explained in the previous lecture, type requirement starts with the keyword type name. And here, I simply use the constraint on shape and pass the template parameter q. This expression will check that the template parameter q is a valid template parameter by substituting it in the shape object, which therefore will call the constraint on shape, which in turn will check if q is a valid arithmetic type or not. So that's all. In the generic functions, I use this constraint now. So let me copy this and type it here. Requires shape constraint with the template parameter u. Similarly here, I use the same constraint but with template parameter v. And now I can compile the code. So right now the template parameters are either integral or floating point type. But when I pass a string template parameter and try to compile the code, here I get the compilation error, that is there's no matching function call to create shape because we are passing a string which doesn't conform to the requirements of shape's template parameter. If I set the diagnostic depth to 2, let's try this here. So here I set the diagnostics depth for concepts to 2, and then compiler gives us more detail that this parameter should be only arithmetic type. That is, it should be either integral or a floating point type. So that's all I wanted to show you in this lecture. See you in the next lecture. Thank you.